Ladies and gentlemen, good morning. Let's continue with our module in heat transfer. We are working out of the textbook of Cengel and Ghajar, 5th edition, and we are busy with the chapter on external forced convection. What we did with the previous lecture is to do a quick revision of our fluid mechanics, or the fluid mechanics that you've done previously, to specifically look at the boundary layer thicknesses and friction coefficients, but to separate and distinguish them between laminar and turbulent flow. So with those same types of equations from previous lectures, we have seen that there are lots of similarities, and by using the same technique that was using for the flow over a flat plate, it is possible to solve the thermal boundary layer thickness for a flat plate, laminar and turbulent, and also to derive some equations for it, the Nusselt number equations. And we've separated it, as I've mentioned, in laminar and turbulent flow. So the previous lecture was quite boring. It was just lots of equations that I've showed you, but we didn't look at any applications. Before we're going to do 3 examples, I would just like to complete the part on the flat plate by also bringing to your attention, and without doing it in detail, to look at the cases where we've got a flat plate, and there are also some theoretical derivations for that, where we've got flow over this flat plate, a certain velocity and temperature, and this flat plate, let me just get some more colors. I need a blue and a red. So in this flat plate, the thermal boundary layer will start there, developing. So that's the thermal one. And then there's a special case where we've got this distance psi, in which there's no heating or cooling. And therefore, the heating and cooling will only start at that point there. So it's an unheated length in the first part. So depending on the Prandtl number, the thermal boundary layer can develop like that, or it can develop like that. So there are also some solutions in your textbook for this specific case. Again, from first principles, you can actually solve that. And then this part of the flat plate is completed with looking at the cases of having a uniform heat flux on the plate. So with all the work up to this section, this temperature was a constant Ts. Okay. The temperature everywhere is Ts, so it is called an isothermal plate. We can also have a case where our plate, inside it there's an electrical heater, for example, like that, which means that the heat flux is constant. However, it doesn't mean that the temperature on the plate is constant. It's 2 different types of problems, 2 different categories, and we are going to look later on in the work, we are going to look at many different cases where we look at the case of a constant wall temperature or a constant heat flux. And the equations in your textbook are equations 731 and 732 that specifically describes the case of a constant heat flux. Right, so to better understand the work that we've done up to now, and specifically the parts where we've looked at laminar flow, turbulent flow, and cases where you've got on a flat plate both, I'm going to do 3 examples trying to make these categories more clear to you. So the first example, let's call it scenario 1, is to look at a flat plate with the following dimensions. This is 5 meters in that direction and 1 meter in that direction. And the plate is an isothermal plate, which means that temperature is constant all over the plate. And over this plate, we are going to have oil flowing over it, and the temperature of the oil is 60 degrees Celsius, and its velocity is 2 meters per second. And the question is to determine the drag force on the plate and to determine the heat transfer rate. Okay. Flat plate, 5 meters by 1 meters. It is at a constant temperature 20. Over it flows oil at a temperature of 60 degrees Celsius and a velocity of 2 meters per second. With convection heat transfer, we are always interested in the properties. We need densities, viscosities, Prandtl numbers, etc., etc. So, where do we get it? Well, we first get it in the tables in your textbook in table A13. But we need to go and look at what temperature we should do it, and for that we use the film temperature, which would be that temperature plus that temperature divided by 2. So it is at a film temperature of 40 degrees Celsius. And at that temperature in your textbook, in table A13, you were able to get all the properties. For those of you who have your textbooks here, please do me a favor and go and try and see if you can get those properties. Because there's something very important that I want to show you and that I want to highlight, because many students are going to get the properties now and then they are going to interpret it not correctly. Okay. So please, if you can look at that, you will see that it says that the density is equal to 876 kilograms per cubic meters. The K value is equal to 0.01444 watts per meter Kelvin. The Prandtl number is equal to 2.962, and the kinematic viscosity is equal to 2.485 multiplied by 10 to the minus 4 meters square per second. Are you all happy with those values? For those of you who have your textbooks here, if I can give you a few seconds. You see all the values? Okay, now I hope some of you have picked it up. This value in your textbook, it's a comma there. So in American units, it indicates 1,000. So this value is not 2.9, it is 2,962. So you're going to make an order of magnitude error, 2 orders of magnitude error, if you use a value of 2.962. So please be careful for that. Make some notes for you in your textbook that you really understand it, and that you do not make that mistake in the error, that you make that mistake in the tests and exams.
So the thermal conductivity is number around 0.1444.
It is 0.1444.
0.1444.
Oh, okay, thanks. 0.144, like that. Yeah, okay. You all happy with that? Okay. So, the thing that we always need to do in these types of problems when we work with convection is to know the Reynolds number. The Reynolds number we are going to base on the length of the plate. That is why I use a footnote there, L. And that would be equal to the velocity multiplied by the characteristic length divided by the kinematic viscosity. The velocity has been given as 2 meters per second. The plate is in length 5 meters, and the kinematic viscosity is equal to 2.485 multiplied by 10 to the minus 4. And the result is a Reynolds number of 4.024 multiplied by 10 to the 4. Okay. This is very important because now you need to think about what it tells you. We said that transition occurs with a Reynolds number of 5 multiplied by 10 to the 5. Okay. So it means that in this case, with our plate, which is 5 meters in length, Okay. The Reynolds number at the end of the plate is going to be that. If the plate was longer, there will be a certain length where there will be, where the Reynolds number would be equal to 500,000 and where the flow would change from laminar to turbulent. So in this case, the flow over the total length of the plate is laminar. Okay, so laminar over total length. Right. Therefore, we can use the laminar equations. There are specific equations which are valid only for laminar flow. And the equations is CF is equal to 1.33 multiplied by Reynolds L to the minus 0.5, which is equal to 1.33. The Reynolds number we have determined is equal to 4.024 multiplied by 10 to the fourth, everything to the minus 0.5, and that will give us a friction coefficient of 0.00663. Okay? If we've got the friction coefficient, it's very easy to go and calculate the drag force. The drag force is equal to the friction coefficient multiplied by the surface area multiplied by rho v squared divided by 2. The friction coefficient is equal to 0.00663. We've determined it just now. The density is 876. The velocity is 2 meters per second, so 2 squared divided by 2, and it gives us a small drag force of 58.1 newtons. Okay? Now the heat transfer rate. So that was the first part of the problem, is to determine the drag force. The second part is to determine the heat transfer rate. To do that, we need to get the Nusselt number and the heat transfer coefficient. The Nusselt number for laminar flow only is 0.664, Reynolds L to the 0.5 multiplied by Prandtl to the third. With the friction factor, everything is a function of Reynolds only. With the heat transfer part, we also have the Prandtl number that also influences the Nusselt number. So it is equal to 0.664 multiplied by the Reynolds number, 4.024 multiplied by 10 to the 4 to the 0.5. The Prandtl number is 2962 to the third. And take note, it is not 2.962, 2.962. And the result is a Nusselt number of 1913. Am I going too fast, or are you with me? You're fine. Okay, the Nusselt number is equal to the heat transfer coefficient multiplied by characteristic length divided by K. The Nusselt number is equal to 1913. Is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity, 0.144, and that gives us a heat transfer coefficient of 55.25 watts per square meter degree Celsius. Now that we've got the heat transfer coefficient, we can calculate the heat transfer coefficient, the heat transfer rate. The heat transfer rate is equal to the heat transfer coefficient multiplied by the area. And in this case, it is T infinite minus Ts, because the temperature of the oil is larger than the temperature of the plate. Okay, the heat transfer coefficient is equal to 55.25. The surface area for heat transfer is equal to 5 meters multiplied by 1. It's 5. Okay, he didn't say in the problem that the oil flows through both sides of the oil, so it's at one side only, and the temperature difference is 60 minus 20, and that gives us a heat transfer rate of 11,050 watts. That's not an engineering answer. An engineering answer is 11.1 kilowatts. Any questions? Yep. Oh, sorry, with the drag force, I didn't insert the area. You're right, so there should be a value of 5 in there. Thank you. Any other questions? Okay. So why is this problem important? This problem is important because if we look at the Reynolds number, we can see that the flow is laminar over the total length of the plate, and therefore we use the laminar equations only. So take note, this equation and this equation, if you go and look in your textbook, it says it's for laminar flow. Okay. Let's look at another scenario which is now similar to this one, but different. And that is scenario 2. Okay. In this case, we've got a house. And the length of that wall is 50 meters, so 50,000 millimeters. And the height is 4 meters, or 4,000 millimeters. We've got a wind blowing over this wall at a velocity of 7 kilometers per hour. And the temperature is equal to 5 degrees Celsius. And the wall is measured on the outside having a temperature of 12 degrees Celsius. Okay, so we've got a house. The temperature of the wind is 5 meters per second. The surface temperature on the outside is measured as 7 degrees everywhere. Those are the dimensions, and we would like to know what is the heat transfer rate through the wall, and we're also going to calculate the drag. Why would this be an important example? Because, for example, in air conditioning and refrigeration, if you want to keep the temperature constant inside the house, you would like to know what will the heat loss be through this wall. Because if you know it through the one wall, then most probably you have it for the other wall also. So this wall and that wall will be a little bit more complicated to determine, but in principle, if the heat transfer rate through that wall is 10 kilowatts, then you need at least 20 kilowatts of heat transfer into the house to keep the temperature constant. So that's a practical example. Again, we need to get the properties, and we get the properties at the average of the surface temperature and that of the environment, and in this case at 8.5 degrees Celsius, and the values are available in table A15, I think. The K value is equal to 0.02428 watts per meter Celsius. The kinematic viscosity is equal to 1.413 multiplied by 10 to the minus 5 square meter per second. The Prandtl number is equal to 0.7340, and the density of the air is equal to 1.25 kilograms per cubic meters. Okay, so let me just repeat the problem. We've got a wall. We only look at this wall of a house. 5 meters in length, 4 meters in height. It's 50 meters in length, 4 meters high. And we've got a cold wind at a velocity of 7 kilometers per hour and at a temperature of 5. When I worked through this problem, I had to adjust some of these values to get it to, so that the problem works out. So it might be that this should be 5 kilometers per hour, I'm not sure, but you can just check that. So that this might be 5. Right, so again, let's determine the Reynolds number, because the Reynolds number is going to tell us what type of flow do we have on the outside of the wall. So the Reynolds number is equal to the velocity multiplied by the length divided by the kinematic viscosity. The velocity in this case is 7 kilometers per hour, so it is 7,000 meters divided by 3,600 seconds to get it to meters per second. It is 7 kilometers, kilo is 1,000, so it's 7,000 meters, and per hour divided by 3,600, that's the velocity in meters per second. Multiplied by the length. Now the length in this case is very long, 50 meters, divided by the kinematic viscosity is 1.413, multiplied by 10 to the minus 5. So the Reynolds number is equal to, in this case, 6.88 multiplied by 10 to the 6. We say that the flow changes from laminar to turbulent when the Reynolds number is 5 multiplied by 10 to the 5. So in this case, the flow will be turbulent. Now that is correct, but it is not really the whole truth. Because of this long plate now of 50 meters, although the Reynolds number at that point there is turbulent, the flow should have started to be laminar always. So the question is, where does it change from laminar flow to turbulent flow? Maybe there. Okay. So that's laminar and that is turbulent. How do we determine that? Well, very easily by just looking at determining the critical Reynolds number as the velocity multiplied by the critical length divided by the kinematic viscosity. So we go and determine where the Reynolds number will be 500,000. Okay, here the Reynolds number is always 0 because x is equal to 0, and then it increases downstream because it's a function of x or L. So the critical Reynolds number in this module we use as 500,000, 5 multiplied by 10 to the 5. The velocity doesn't change. We still want to know at 7 kilometers per hour, multiplied by the critical length, divided by the kinematic viscosity, 1.413 multiplied by 10 to the minus 5, and that gives us a critical length of 3.633 meters. So, if you want to see the bigger picture in terms of this plate, we consider this as a flat plate, 5 meters. I know I made a mistake here somewhere. Oh, sorry, 50 meters, yeah, 50 meters. So it's 50,000 millimeters, like that. Okay. So on a length of 50 meters, 5 meters will be about 1/10 of this length. Do you agree? So 5 meters will be about there. So if we try to plot it by scale, 3 meters will be approximately there. Thus, so if you can imagine this boundary layer, you're going to have laminar flow up to that point, and then the flow is going to be turbulent. So you only have laminar flow in this part. But the rest would be turbulent. So, as an engineer, you're going to look at this and you're going to say, the laminar part is negligible in terms of the total picture. It's an assumption. Okay. So the assumption is we've got turbulent flow only. And for turbulent flow only, there's a set of equations that you can use. And that's the equations that we're going to use now. So it starts by, for turbulent flow, the average CF is equal to 0.074 divided by the Reynolds number L to the fifth. Okay, that is equation 7.15 in your textbook. Take note, it's for turbulent flow only. So if we go and put in the value there, I'm quite sure you can do it yourself, 0.074 divided by the Reynolds number. There's the Reynolds number. Just put it in there, and then you can get that the CF value is equal to 0.003175. The drag force is then equal to CD multiplied by the area, rho V squared divided by 2. Sorry, let's make that a CF. Can use CD if you want to. Okay, so CF, there it is. The area is 50 multiplied by 4. Okay, so that is 50 multiplied by 4. Okay, the density is 1.25. Okay. The velocity is 7,000 divided by 3,600 divided by 2. So you can go and do the substitution yourself, and that works out as a small value of 1.5 newtons. Very small drag force. Right, but we are more interested in the heat transfer. So for the heat transfer, again, we go and look at the equations, and we select the equation which is for turbulent flow only. Turbulent flow only, and that is equation 722 in the textbook. I'm quite sure you can do it yourself. There's the Reynolds number, 6.88 multiplied by 10 to the 6. The Prandtl number is 0.7340. Okay, you can put it in there, and then you can get that the Nusselt number is equal to 9852, the non-dimensionalized heat transfer coefficient. What does it mean? It means that the heat transfer will be almost 9,900 times more than that of conduction only. So the convection causes that the heat transfer rate increases with almost 9,900 times. That's what it means. The Nusselt number is also equal to the heat transfer coefficient multiplied by the length divided by K. There's the Nusselt number. The length we have is 50 meters. The thermal conductivity we have, and from that we can get the heat transfer coefficient as equal to 4.784 watts per square meter degree Celsius. Now that we've got the heat transfer rate, we can determine the heat transfer coefficient, we can determine the heat transfer rate. The heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by Ts minus T infinite. In this case, the plate is at a higher temperature than that of the free stream, therefore we just write it the other way around. The heat transfer rate is equal to 4.784. The area is 50 multiplied by 4. There's a temperature difference which is equal to 12 minus 5. 12 minus 5, and then we can get that the heat transfer rate is equal to 8,698 watts, which is equal to 8.7 kilowatts. So, the air conditioning system or the heating system in this house, just because of the heat transfer rate through that one wall, would require about 9 kilowatts of heating that you need to do for this one and for that one. So you can multiply it and you can get approximately 18 kilowatts of heating required only for the two walls, the long walls. Right, do you understand? Okay. Yep.
We have used the general equation to solve for CF, where we take into account the laminar flow and the turbulent flow.
Yes, that is exactly what I want to address now. So the question is, could we not have used the other equation? And the answer is yes. The other equation is just more work. Okay. But this is a good engineering assumption to say that it is turbulent flow only. Because what is confusing to students is they look at these equations of turbulent flow only in that section, and then they ask, but where do I use it? Because I can't actually use it anywhere. So you use your judgment as an engineer in some cases to estimate the heat transfer. Okay? Well, in this case, you're going to say, I'm going to neglect that and consider the total boundary layer as turbulent. Let's suppose your wall was smaller than, it was just 3 meters. It was just 3 meters in length. You know you should use laminar equations, then you should use the equations on that side. So laminar only. So for these are turbulent only, and the ones that you are interested in, we are going to do now is scenario 3. So let's look at scenario 3. So with scenario 3, again, is a house. But in this case, it is not that long. That is 5 meters and 4 meters. And we've got the wind blowing over the wall, the temperature of 5 degrees Celsius, the velocity 10 kilometers per hour, and again the surface is measured as 12 degrees Celsius. It's an isothermal surface. It's 12 degrees Celsius everywhere. Right, so we need to get the properties. We're going to get the properties at 5 plus 12 divided by 2. That is at a temperature of 8.5 degrees Celsius. Okay, and this temperature is the same as that temperature, and for both it's air. So these properties, okay, are the same. Okay. So again, let's determine the Reynolds number now to see if the flow is laminar or turbulent. So the Reynolds number is equal to VL divided by the kinematic viscosity. The velocity is 10 kilometers per hour. So it is 10,000 meters divided by 3,600 seconds, multiplied by a length of 5 meters divided by the viscosity 1.413 multiplied by 10 to the minus 5. And that will give us a Reynolds number of 982,936, which again says the flow is turbulent. Okay. So that's all good and well to know the flow is turbulent, but we want to know where do the flow changes from laminar to turbulent, because we need to think which decision are we going to make. Can we consider everything as turbulent? We've already seen that we cannot consider everything as laminar. Okay. So in this total length of 5 meters, we know the boundary layer thickness does that, and we know that the flow is turbulent at the end of the wall. We want to know where does it change from laminar to turbulent. So for that we calculate, we use the critical Reynolds number. The critical Reynolds number is the velocity multiplied by the critical length divided by the kinematic viscosity. The critical Reynolds number is 5 multiplied by 10 to the 5. It's equal to the velocity is 10,000 divided by 3,600 meters divided by the critical length, divided by the viscosity, 1.413, multiplied by 10 to the minus 5, and that gives us a critical length of 2.543 meters. Right, making sketches is important because it helps you to get a better perspective on things. So this plate is 5 meters in length. We know the flow there is turbulent, and this tells us the flow is going to change from laminar to turbulent at 2.543 meters. So that length there is laminar flow, and that length is turbulent flow. So this is an obvious case where we cannot say we're going to make an assumption of turbulent flow right through, because it's 50-50 about. Okay. Therefore, this is now scenario 3, where we look at the equations that takes into consideration the laminar part. And for that, the CF will be equal to 0.074 divided by Reynolds to the fifth minus 1742 divided by Reynolds L, and that is equation 7.17. Right, it's two constants, and we need to put in the Reynolds number there. The Reynolds number, there it is. It's equal to 982,932. We can do this calculation and then determine that the friction coefficient is equal to 0.002913. The drag force is then equal to CF multiplied by the area, rho v squared divided by 2. Okay, let's put it in, write it out, 0.002913 multiplied by the surface area, in this case, is 5 multiplied by 4, it's 20 square meters, divided by the density, or multiplied by the density is 1.25, something like that, multiplied by the velocity again is equal to, what was it again, 10,000 divided by 3,600 squared divided by 2, and from that we can determine the drag force as 0.218 newtons. Very small. This is for the drag force. Now we need to get it for the heat transfer. For that we need to determine the Nusselt number, and the Nusselt number is now the equation that takes into consideration the laminar part. So it is equal to 0.037 multiplied by Reynolds to the 0.8 minus 871 multiplied by Prandtl to a third, and that is equation 724 in your textbook. Right, the Reynolds number, there it is. Okay, just put it in. The Prandtl number, there it is. Just do the substitution, and then we get that the Nusselt number is equal to 1,291. So the heat transfer is being enhanced by approximately almost 1,300 times in comparison with conduction only. The Nusselt number is equal to the heat transfer coefficient multiplied by length divided by the thermal conductivity. The heat transfer coefficient is what we are interested in. The length we've got, K we have, and from that we can calculate the heat transfer coefficient as equal to 10.09 watts per square meter degree Celsius. The heat transfer rate is now equal to the heat transfer coefficient multiplied by the area, Ts minus T infinite. The heat transfer coefficient is equal to 10.09. The surface area of the wall is 20 square meters. The surface temperature is 12, and that of the air is 5, and the result is a heat transfer rate of 1,412 watts, which is equal to 1.4 kilowatts. Thus, to summarize, the equations in your textbook for a flat plate, there are lots of equations. It's very easy to get confused. With all of these equations next to it are also given typically the Prandtl number range that the equation is valid in and the Reynolds number range. But in general, you can divide the equations into 3 groups. The first group is where the flow is laminar over the total body. Then you use the laminar equations. They are very easy and simple. The second group, you don't have to do if you don't want to. Okay? It is just more work to follow scenario 3. But if you calculate it and you see that the end of the plate is turbulent, then obviously there must be a transition from laminar to turbulent somewhere. If it is small, like in this case, you can say it's negligible, and you use the turbulent equations only, that one and that one. Okay. If you are, however, of the opinion it is not small and it is not negligible, for example, like in this case, where the transition is now approximately halfway over the plate or the wall, then you can use the equations where you take the laminar part into consideration, but the flow at the end is always turbulent. And I think that summarizes the work on a flat plate. There's a question there at the back.
So, how small must that laminar part be for us to just say it's negligible?
Well, it is, so the question is, how small should the laminar part be to say it is negligible? It's an engineering judgment question, so there's not one good answer for that. Let's suppose you just want to see an order of magnitude approximately. Then making that assumption would really not influence your results. But if you're maybe competing against competition for supplying lots of buildings like this with an air conditioning system, if you size it too big, then you're going to not to be competitive in terms of your competition that size it's better. So if you know more accurately, then you would be competitive. So in that case, I will definitely take it into consideration. Also remember, and you're going to see it right through this module, that heat transfer coefficients rarely are accurate to plus or minus 10%. In most cases, it's plus or minus 20%. Now, if you take into consideration an uncertainty of plus or minus 20%, then making this assumption in this case is an excellent assumption. But I cannot give you a good rule that you can always use. That, unfortunately, is not available. Any other questions, ladies and gentlemen? If not, thank you very much, and then we'll see each other with the next lecture.